presenting his work conducted in one of our laboratories under my guidance as well as the guidance of my close colleagues. Stefania, please tell us what you have done so that we can hear your results. Thanks a lot. Please go ahead.
Thank you. Before I start my presentation, I would like to acknowledge the guidance and the efforts put in by Professor NNP and and also Francisco. So, yeah. So my thesis statement is diagnosis of the existing centrifugal test bed, and also the implementation of a directed stream jet technique, which is actually used to control the boundary layer at the inlet of the diffuser. So, okay, I'm going to talk about the introduction, experimental apparatus, the diagnosis, and the various techniques to control and the measurement of performance characteristics of the centrifugal test bench. Then a detailed description about the directed stream jet technique, then the dimensioning of the new parts in the centrifugal test bench. Conclusion. So, as you all know, necessity is the mother of all inventions. So, there was a need arise when the fluid scientists were trying to increase the efficiency of hydraulic turbine. So, there was a debate going on whether the kinetic energy of the moving fluid from the blades, that energy can be converted to some useful work. So, there comes this purpose of the diffuser. So, if you have the diffuser, we can utilize this kinetic energy of the fluid which has come out of the turbine, and if you keep it at the downstream, you can increase its efficiency. And as you all know, the major principles behind these turbo machines are Newton's second law of motion and Euler turbo machine energy equation. And it is very important that even the change of 1% of pressure recovery coefficient can be equivalent to 1/10 of a percentage of efficiency improvement. So we are concentrating majorly on the pressure recovery coefficient. Okay. Then a brief description about the experimental apparatus which is in the lab, the lab, turbo machine lab. Now I'm going to explain in brief the major parts. One is the DC motor, which is used to drive the blower, the centrifugal blower. Its range is from 500 RPM to 500 RPM to 5000 RPM. But its capacity runs at max at 3000 RPM, and is controlled by servo motors. And then comes it works with the principle of Fleming's left-hand rule. And then comes mouthpieces and transducers. The mouthpieces and transducers are kept so that the mouthpiece works with orifice principle, that is differential pressure. So it creates differential pressure between the atmospheric condition and the inside. So the air flows from a region of high pressure to low pressure. Then the transducers. Transducers are an important part because they help in the conversion of physical signals into digital values. And then comes the diffuser and inlet section, which is of area of interest. So the diffuser is where the entire thing is concentrated, where we are going to concentrate on the boundary layer. And then comes the scanning valve. Scanning valve is nothing but it is an interface where the pressure readings are converted to digitally, and we can measure it through the lab software. And next is the thermocouple. Thermocouple is a sensor which is used to measure temperature, and it works on basically heat storage. So before implementing this technique, we have to have a knowledge about the theory behind the boundary layer. So the major equations governing this boundary layers are first the Navier-Stokes equation. So in the Navier-Stokes equation, considering it as an incompressible flow, So our concentration is on the shear stress component that goes dou by dou one partial derivative. So as you can see on the left hand side, it is the material derivative of the velocity components, and the right hand side there is a pressure gradient component and also the stress component. So our entire part on controlling this boundary layer, we have to focus on the viscous stress component, which is the turbulent inducing component, which is nothing but mu plus rho L square dou u by dou one. So we have to reduce this. If we reduce this, the transition from we will delay the transition from laminar flow to turbulent flow, and we move the stagnation flow. So that is our whole idea. And then the Bernoulli equation. So the Bernoulli equation is where the useful work we get can be obtained. This relation between the velocity component and pressure gradient. Then comes the most important parameters with which we have to assess the diffuser. That is the pressure recovery coefficient and the diffuser effectiveness. The pressure recovery coefficient is nothing but it's a ratio of the pressure difference at the outlet and the inlet to that of the kinetic energy of the fluid, which is nothing but half rho u square. And then comes the diffuser effectiveness. It is nothing but the pressure recovery coefficient at normal conditions to that of the ideal conditions. So the ideal conditions is where the maximum coefficient of performance is achieved with a particular area expansion ratio. So that is the ideal case. And so the CPI has a relation with correlation with the area ratio. So 1 minus 1 by area. Okay, and geometrically speaking, the diffuser has many geometrical parameters, but the main geometrical parameters which affect its performance are the passage divergence, the approach length, and the area ratio. And the velocity comp and inlet airflow also contributes a little bit. So Reynolds number and Mach number of the air also, but those contributions are there. And the typical geometrical feature which we have to reduce in order to control the boundary layer and increase the efficiency of the diffuser is the inlet blockage factor. So this inlet blockage factor, we have to reduce it. It's nothing but the 1 minus effective area fraction. So this effective area fraction is nothing but it's 1 by a integral of u by um du, where u is the initial velocity, um is the maximum velocity, and a is the overall area. So we have to increase this effective area fraction and reduce this inlet blockage factor. Okay, before doing that, the existing centrifugal test bench was not in a proper condition because due to heavy wear and tear, there are a lot of inaccuracies which were obtained. So first we tried to analyze where these inaccuracies were coming from. So the problems we encountered mostly were there were error in the pressure values and also in the torque meter. So first we theoretically calculated the pressure values using Bernoulli equation applying at the mount piece, and we found out there was difference, it didn't coincide. And then we did an experimental analysis using a pressure measuring device. This pressure measuring device is of very high accuracy and precision from TSI instruments. So with this we checked the pressures at the static pressure and also the total pressure. So the static pressure transducer also had some issues, and also the total pressure transducer also had some issues. And we did different conditions at different pressurized conditions. We took the values, and there is also a possible replacements for those sensors proposed in my thesis. So these are the results. In case one, the dampener is nothing but the output of the external centrifugal test bench. If you close it, the centrifugal test bench will get pressurized. So when we in the case one, we closed it for 95%, and then we took the values for different RPMs, 2734 and 1791. So what we obtained was the LabVIEW software static reading was different from the pressure measuring device reading. The very less, like 0.46 and 0.119, which was okay. But when considering the case 2, when the damper was fully closed, when it was at the maximum pressurized zone, the error percentage were significant, as you can see, 6.8% and 12.9. So this was repeated for both static transducer and also a total transducer. Now comes how to control the boundary layer. So before controlling the boundary layer, I studied and analyzed different techniques so which one is the best suited for controlling the boundary layer and the diffuser. So of course there is a necessity for controlling the boundary layer because we have to remove the low momentum layer in order to control the boundary layer, in order to increase its performance. Four methods were studied. In that, the first method I studied was tangential blowing. So this is one of the successful methods which is used in aerospace applications and those kind of things. But the only problem is the blowing coefficient, the blower efficiency, and it is a little bit complicated. This technique is very cost consuming also. And then comes the suction method. The suction method is nothing but sucking the low momentum layer which is attached to the wall. So it is that kind of method. This method is also very successful, especially in airfoils where you put slots and put vacuum pump and sucking the boundary layer. But the problem is again electric consumption of the vacuum pump, the cost of the vacuum pump and everything is more. So that is another disadvantage. Then the vortex generator method. So the vortex generator method is nothing but in the free stream from the potential flow you induce energy to the boundary layer region through eddies formation and those kind of things. But it is very complicated because to predict the scale of turbulence it is not so easy. There are still large eddy simulations, Kolmogorov scale, on-Karman scale, and it is very complex, the physics behind it. So that is another disadvantage. So accurately you cannot measure in terms of magnitude how we can control the boundary layer. But it is also very successful in applications like aerospace technologies. And then comes the method which I have chosen, which is dynamic forcing method. This is an easy method which is very cost efficient, where we use an acoustic speaker like of a particular specification, and we control it to a frequency regulator and send shock waves and vibrations. Through this, the incoming air flow is obstructed and the boundary layer is cooled up, and we can control it. So this is a diagram. This is the acoustic source, and this is the like an orifice cavity, that is the slot through which the vibrations are sent, the waves are sent. It interacts with the incoming flow air, and this kind of flow distribution will happen. It is nothing but uniform flow versus circulation. So this is that kind of flow field will happen if you do it periodically. This kind of ring vortex in controlled instances can be done. Okay. And then to understand the different parameters, we did some measurement of the performance characters of the centrifugal test bench. The centrifugal test bench has a lot of devices, and the measurement system is basically we have transducers connected to the LabVIEW software, and then the procedure for the acquisition of the quantities is nothing but we start the machine and we start running the program, the LabVIEW .py program, and we adjust the pressurizing zone and QH characteristic is very important. From that we can calculate the velocity, pressure values, and I did it for 5 different speeds, and we can see the influences. This is a particular result from one of the RPMs. You can see a trend that the mass flow rate decreases when you pressurize it more and the head increases when the opening of the damper is closed completely, and also the efficiency increases for that. The velocity potential function, the stream potential function remains almost same, and for a fully closed case it slightly changes. This is a QH curve, how the pressure and the mass flow rate are related. This is a trend line.
You don't have to fly, just speed up a little bit.
Okay.
So,
Okay. So this is a plot showing how the velocity varies with different openings of the damper. So at very specialized zones, what is the velocity? This can be calculated with the mass flow rate. Mass flow rate is equal to density area into velocity. So with mass flow rate and you know the density and the area of the diffuser, you can calculate velocities. Okay, and then this is a detailed design procedure of how a director stringent technique is applied at the limit of the diffuser. So I studied various literatures, and from one of the literature work, I found out that they have applied this technique for this specific kind of dimension of diffuser. As you can see, this is the channel, and this is the velocity profile, and that is the slot. They have mounted it, the JBL 21188-inch speaker model subwoofer type has been mounted on it, and it is being controlled through a frequency regulator electrostic controller. So the shock waves are sent, the vibrations are sent in, it affects the airflow, and in that way the ground layer is moved up. And this is nothing but the static pressure distribution versus forcing error. This is at various approach lengths, that is the approach lengths. What is the CP performance value and at what angle of the diffuser that they are obtained. And these watts show that the input electric power. As you can see, for a very less input electrical energy itself, you can find out there is a lot of gain in the CP performance. So at different watts, what are the gains? So we can see through this diagram. And here there is a CP of exit versus frequency. So at 100 frequency, you can see a CP achieves its maximum, and then it reduces. This is the pattern you can see. So the most important thing which I studied from this literature is that there is a 45%:1 return to the return ratio. That is, we get that much percentage of input electric power as return, and we spend very less input electric power, and we get in terms of the output very lot. So these are some of the reference values at the diffuser of the experimental setup, at what conditions and at what dimensions they have channelized and they have got these results. So yes, with these dimensions, I scaled up to our existing centrifugal experiments, and I modeled the technique. So before going there, in this technique, the important component is the speaker. So the speaker, you have to know about the design of speaker and how the speaker is designed, and some important terms related to the speaker. So the important terms related to the speaker are, one is the three most important things are equivalent volume, free air resonance, and Q hat. Equivalent volume is the amount of space which is required for the sound waves to travel, and the free air resonance is nothing but at what frequency it matches with the natural frequency, and the resonance happens, reverberation happens. And Q factor is nothing but the quality of the sound, the quality of the waves. So it is nothing but ratio of the output to input impedances. Then we have to study also the really small parameters, which are nothing but this is a sealed type of a speaker. This is the best kind of a speaker you can choose for this kind of a direct exchange technique out of all other speakers. In this, you have to know about the effective bone diameter in dimensioning that, mounting depth, magnetic diameter, magnetic height, and linear excursion. So the linear excursion is also a very important geometrical feature. If you place it in wrong dimension, you cannot get the acquired results. So this is the engineering diagram of the speaker, the CAD model, and
if you could go to the conclusions.
Yeah, just one second. So this is the dimension of the part. This is the like, outline 2D sketch, and this is the 3D front projection of the entire test bench with this technique, mounting speaker intersection layout. So conclusion is that this is a new concept which is used to control the boundary layer, and it is being in developing stages. And at sufficiently high excitation levels, there is a superb dynamic separation, and we can easily control it. And it is very insensitive to external parameters. And a simple electrostatic model is also developed, which accurately predicts the DSD net velocity performance. And also, this uses an acoustically driven arrangement, and it is time average, so it can easily control the momentum coefficient, that is momentum of each stream to the next stream momentum, so it can easily control it. And this is a non-optimized diffuser, so it has